every chemical substance has its own unique chemical formula. And a unique chemical formula of a substance allows us to derive a lot of information that can be used as conversion factor that will allow us to solve some of the basics problem in general chemistry. For an example, given acetic acid, and the chemical formula of acetic acid is CH3COOH. And from this chemical formula, we can calculate molar mass, which is 60.05 gram per mole. So this is an example. And from the information we have seen above, there's many conversion factors that we can derive from it that will allow us to solve many basic problems here in general chemistry. In chemistry, students are expected to be able to do the following. Let's say we give you certain amount, gram, of acetic acid. We can then ask students to find how much of it, what is the amount of carbon that we will have, what is the amount of hydrogen that we will have, and what is the amount of oxygen that we will have. For an example, given certain amount of acetic acid, how many grams of carbon do we have from that amount? And how many mole of carbon do we have from that amount? And how many atoms of carbon do we have from that particular amount? And similarly, we can do the same thing. We can ask for the amount of hydrogen in gram or in mole, and all atoms of hydrogen as well. And similarly for oxygen. And these are some of the basic problems the student need to be able to do in general chemistry courses. And to be able to do that, we need to go over the different conversion factors from the chemical formula. The first types of information that we can get from the chemical formula is something that I referred to as the atom ratio. Once we are given the chemical form of a substance, we can draw a lot of atom ratio from the chemical formula. For an example, looking at the structure of acetic acid, for every one molecule of acetic acid, we will then see there are 4 hydrogen atoms. So basically, every molecule of acetic acid has 4 hydrogen atoms. That is one piece of information. And from that piece of information, we can draw the following relationship. So one molecule of acetic acid, CH3COOH. There are 4 hydrogen atoms, or we can say over 4 hydrogen atoms. And similarly, we can also draw the relationship between the entire molecule to the amount of oxygen. And here in this case right here, again, for every one molecule of acetic acid, there will be 2 oxygen atoms. So we can draw a relationship between the entire molecule to the individual atom that is found in this molecule. And in addition to that, we can also draw the relationship among the atoms in the molecule as well. For an example, for every 4 hydrogen that we have, there are 2 oxygen atoms that will be found in acetic acid. So again, for acetic acid, for every 4 hydrogen, there are 2 oxygen. So from there, we can also write this following relationship. 4 hydrogen atoms over 2 oxygen atoms. And similarly, we can also draw a relationship between the hydrogen to the carbon as well. So basically in this case right here, for every 4 hydrogen atoms, there will then be 2 carbon atoms. And we can also draw a relationship between the carbon and the oxygen as well. So for every 2 oxygen atoms, there will be 2 carbon atoms. So these are the types of conversion factor that we refer to as the atom ratio. So the ratio of the different elements that make up the chemical substance. The second types of information that we can also derive from the chemical formula is something that we now refer to as the mole ratio. Now, we have learned already that we can convert atoms or molecules into mole. And How will we be able to do that? It basically by taking them and divide them by the Avogadro constant. So here, in this case right here, we can convert from molecule into mole. And we can also do the same thing to convert the amount of hydrogen into mole as well. And because we are both dividing them by the same value, therefore ratio-wise they would be the same. So basically we can now convert this into 1 mole of acetic acid over 4 mole of hydrogen. So the value up here would still be the same when we convert the individual atom or molecule into mole. The ratio would be exactly the same. And for an example, the conversion factor from above, we can now convert this into mole ratio as follows. 1 mole of acetic acid. So we convert in molecule into mole. And now we can convert atom into mole as well, over 2 mole of oxygen. And here in this case right here, oxygen is O. It's not O2, but it's O, because we are referring to the oxygen in this substance. But we are not referring to oxygen that exists by itself. So therefore the chemical formula would then be simply 1 oxygen. And similarly, we can convert hydrogen atom into mole and oxygen atom into mole, and the ratio would still be the same thing. So we can also write the following: 4 mole of hydrogen over 2 mole of oxygen. And similarly, 4 mole of hydrogen over 2 mole of carbon. And for this one, 2 mole of oxygen over 2 mole of carbon. So the atom to atom ratio can be converted into the mole to mole ratio directly, and their value would still be the same thing. And the next types of conversion factor that we can also get from the chemical formula is something that I refer to as the mass ratio. Now we know that we can convert mole into mass by using the molar mass as the conversion factor. And if we were to now convert the mole of acetic acid and the mole of hydrogen into gram, then we will have the following: 1 mole of acetic acid, weight 65.05 gram of acetic acid, and 4 mole of hydrogen, then weight 4 gram of hydrogen. So as you can see, we can convert mole into gram and mole into gram. And now we have the following mass ratio: the mass ratio between the mass of the entire substance to the mass of an individual element that make up that substance. And similarly, we can also convert this into the mass ratio as follows: 60.05 gram of acetic acid over 2 mole of oxygen, and 2 mole of oxygen weight 32.00 gram of oxygen. And similarly, we can convert mole of hydrogen and mole of oxygen into mass in gram as well, and we have following: for 4 gram of hydrogen over 32 gram of oxygen. And we can do the same thing for these 2 other conversion factor as well. So this is now at the mass ratio. Now, it's really important that we are able to come up with this conversion factor right here. For an example, when will we get to use this conversion factor? This conversion factor right here is helpful. Let's say if we were to give you certain amount, certain gram of acetic acid, and we ask a student how many gram of oxygen would then be found in that amount of acetic acid, then you can use this conversion factor right here to solve that problem. And similarly, if we were to ask for gram of hydrogen from a given amount of acetic acid, then you can use this conversion factor right here to solve this problem. And when will we use this conversion factor? Let's say that you are being told that there are certain amount of carbon or certain amount of hydrogen in acetic acid. How much mass of oxygen would there be? Then again, you would use this conversion factor right here, because this conversion factor will allow us to convert between the mass of hydrogen to the mass of oxygen in acetic acid. So those are the example of when we'll be able to use this conversion factor to do some of the basic calculation here in general chemistry. And in addition to these three basic types of conversion factor right here, there is another one. And I'm going to call this one right here the mixed conversion factor. The mixed conversion factor is a type of conversion factor when we mix mole and mass ratio together. For an example, let's say here we have this conversion factor. 1 mole of acetic acid over 4 mole of hydrogen. So what we can do is we can keep the amount of acidic in mole, but now change the amount of hydrogen from mole into gram. So now we have mole of acetic acid over gram of hydrogen. So this will be a mixed conversion factor because it involves the unit mole of one substance and mass of another substance, which is as follows. So in this case right here, we can keep the mole the same, 1 mole of acetic acid. And here on the bottom, rather than having 4 mole of hydrogen, we know the 4 mole of hydrogen will weigh 4 grams. So in this case right here, I can now put 4.0 gram of hydrogen. So again, this is something that we call the mixed conversion factor. And this is a very neat and useful conversion factor right here, and will allow us to convert between the mole of a substance into the gram of an individual element that make up that substance very, very quickly. And similarly, for any of the conversion factors that we seen above here, we can mix them together and draw a relationship among them. Another example would be as follows. So here in this case, let's say we have this set of conversion factor. I will mix them together as follows. I'm going to keep the mole of oxygen the same and now convert the mole of acetic acid into gram. So here in this case right here, 1 mole of acetic acid, which weighs 60.05 grams. So I can write 60.05 grams of acetic acid. And now on the bottom, rather than putting 2 mole of oxygen, we know that 2 mole of oxygen would then weigh 32 grams. So therefore on the bottom, 32.00 grams of oxygen. So that is another example of the mixed conversion factor. So in the end, the more conversion factor that we can come up with, then the faster that will allow us to solve problem. Sometimes certain problem would require 4 or 5 steps to be able to solve it if we were to use the traditional method. But if we were to be creative and learn how to use conversion factor correctly from the chemical formula, we can now solve that problem in a much faster way, which may take a step or 2 steps rather than 4 to 5 steps. For an example, these are some of the basics problem right here that we expect students to be able to do. For an example, how many mole of oxygen will be found in 18 mole of CO2? So in this case again, let's solve this by using dimensional analysis. Our starting unit is 18 moles of CO2, and the wanted unit, in this case right here, is the mole of oxygen. So we have been asked to convert between mole of CO2 or mole of a substance into mole of oxygen or an element that make up the substance. So in order to do this conversion right here, we need to have the relationship between CO2, mole of CO2 to mole of oxygen. And we will then know that in CO2, for every 1 mole of CO2, there are 2 mole of oxygen. And that will be the conversion factor that we will need to use. And now to set this up, we start with 18 mole of CO2. And now we will then see for every 1 mole of CO2, which is something we have to put on the denominator, so the unit mole of CO2 can get cancelled out. And on top, there are 2 mole of oxygen. And now this will get cancelled out, and this is equal to 36 mole of oxygen. And that will then be our answer. Now, in this case right here, we are keeping the answer the way it is, and we do not round on based on sig-figs. And in fact, we actually do round based on sig-figs, but we just have to keep in mind that this value right here are exact value. The atom to atom ratio or mole to mole ratio from the chemical formula is exact. And now let's try the next problem. Determine the number of mole of oxygen in 1.7 mole of calcium carbonate. So in this case, we start out with a mole of calcium carbonate, and we're asking to convert this into mole of oxygen. So our starting unit is then 1.7 mole of calcium carbonate. And we need to convert this into mole of oxygen. And we would then see that in calcium carbonate, for every 1 mole of calcium carbonate, there would be 3 mole of oxygen. And that will be the conversion factor that we have to use. So in this case, where for every 1 mole of calcium carbonate, there will be 3 moles of oxygen. And again, this oxygen right here is O, but not O2, because we are referring to the oxygen in a substance, not the oxygen that exists by itself. So here in this case, this would then equal to 5.1 mole of oxygen. And we will be rounding this answer right here to 2 sig-figs. And the reason why this value right here have 2 sig-figs. This value right here has infinite amount of sig-figs, since these are exact value. Again, the ratios of atom in a chemical formula are exact. And now the next one. Determine the number of mole of hydrogen in 1.4 mole of sulfuric acid. So in this case, we are starting with 1.4 mole of sulfuric acid. And we are asked to then convert this into mole of hydrogen. And we have seen here, based on the chemical formula, for every 1 mole of sulfuric acid, there are 2 mole of hydrogen. So therefore, we will be putting 1 mole of sulfuric acid on the denominator. And on top, we have 2 mole of hydrogen. So this will then equal to 2.8 mole of hydrogen. And the answer will then be rounded to 2 sig-figs. Again, this ratio right here has infinite amount of sig-figs, send the exact value. And on this page right here, on this table, it summarizes some of the basics calculation that we expect students to be able to do in general chemistry. For an example, let's say we start out with a mass of a compound or a substance. Students are given certain mass of a substance, and students are then asked to find the mole. How many mole of that substance do we have? We will then see that to be able to convert between mass of a substance into mole of a substance, it's easy, because we can use the molar mass of the substance as the conversion factor. And once we have mole of a substance already, we can use the ratio, the mole ratio between the compound and the element to convert this into mole of the element. And once we have the mole of the element already, we can also apply the next one to get the mass of the element. But to be able to convert between mass of a compound into mass of an element, it involves this as much step right here. 1 step, 2 step, 3 step to be able to do this conversion. However, if we were to learn how to use conversion factor and learn how to apply the mixed conversion factor in here appropriately, then we will be able to do this, solve this kind of problem right here in a much shorter amount of time. But being able to convert between the mass of a compound into a mass of a constituent element that make up that compound is the types of basic calculation that we expect students to be able to do. And this will be the solution map to the long way how to solve this kind of problem. But again, we can solve this in a faster way if we were to learn how to use the mass ratio of the substance and the element as conversion factor. Let's now try this problem right here. How many grams of sodium are present in 15 grams of sodium chloride? So we can see in sodium chloride, there's sodium in it. And if you were to now have 15 grams of sodium chloride, how many grams of it would then be the mass of sodium? So in this case, let's solve this by using dimensional analysis. Our starting unit is 15.00 gram of sodium chloride. And the wanted unit would then be gram of sodium. And again, we are asked to convert between the mass of a compound to the mass of an element in the compound. So first, I'm going to show you two ways how to do it. We're going to do this the long way and the shorter way. The long way is as follows. Starting from the mass of the compound, we convert this into mole of the compound by using its molar mass. And once we have the mole of the compound ready, we can convert this into the mole of the element that we are interested in. In this case, the mole of sodium. And once we have mole of sodium already, we can use the molar mass of sodium to get into the mass of sodium. So let's try this long way, starting with the mass of the compound, which is 15.00 gram of sodium chloride. And now we have to apply the molar mass of sodium chloride. And molar mass of sodium chloride is 58.44 gram of sodium chloride. In this case, we have to put this on the denominator. And on top will be 1 mole of sodium chloride. And we will then see that for every 1 mole of sodium chloride, there will be 1 mole of sodium. So this is the mole to mole ratio right here that we get from the chemical formula. And now for every 1 mole of sodium, its mass is 22.99 gram of sodium. And the answer will then equal to 5.901 gram of sodium. And we have to round the answer to 4 sigma. So this would be the long way, how we would convert the mass of sodium chloride into the mass of the sodium. Now this would then be the shorter way right here. Starting from the mass of sodium chloride, we can now apply the mass ratio between sodium and the mass of sodium chloride. And we will then see that the molar mass of sodium chloride is 58.44 gram of sodium chloride. In this 58.44 gram of sodium chloride, 22.99 gram of it would then be the mass of sodium. And again, this is the conversion factor that we would obtain once we have learned how to use the mass ratio. And now we can see that will allow us to solve for the mass of sodium in just one step. And that will then equal to 5.901 gram of sodium as well. So this is a much more effective way of solving for this kind of problem. And for number 2, how many grams of chloride are in 15 grams of sodium chloride then? So here in this case right here, we have done seen already that there are 5.901 gram of it is the mass of sodium. So the rest will then be the mass of the chloride. But let's assume we don't have this answer yet, and let's solve this problem independently using this shorter way. So here in this case right here, starting from 15.00, let's change this at 20 to make sure it's consistent, gram of sodium chloride. And now again, we can see the molar mass of sodium chloride, 58.44 gram of sodium chloride. The molar mass of chloride, there's 1 mole chloride in here, in every formula unit of sodium chloride. And 1 mole chloride will weigh 35.45 gram of chloride. So here in this case, this would then equal to 9.099 gram of the chloride. So that's how easy it is for us to solve to solve this kind of problem. And now let's try another example. Carbon with the chemical formula of C10H14O, it is the main component of spearmint oil. And if we were to have 55.4 grams of carbon, what would be the mass of carbon in it? So here in this case right here, let's solve for this problem. The starting unit here in this case right here is 55.4 grams of carbon, and carbon is C10H14O. And the wanted unit in this case right here is gram of carbon. So we can see that we are asked to solve from mass of a compound to mass of an element that make up this compound. And we have seen already that we can use the mass ratio to solve this problem. And we'll be able to do that in this one step. So in this case, starting with 55.4 grams of C10H14O. The molar mass of carbon is 150.1 grams of carbon. And now for every 1 mole of carbon, there are 10 mole of carbon. Each mole of carbon is 12.01 grams. So basically 10 mole of carbon will then be 120.1 grams of carbon. And now we can see the answer will then equal to 44.3 grams of carbon. So notice how quick it is for us to solve this kind of problem right here once we have learned how to use the mass ratio correctly. And I will also show the longer way of how to do this. So this would be the short way. And now let's go over the long way of doing this. The long way of doing this is to start from the gram of carbon, convert this into mole of carbon. And once we have mole of carbon already, we will then see for every 1 mole of carbon, there are 10 mole of carbon. So I'm using the ratio of the element between carbon to carbon to convert this into now mole of carbon. And once we have mole of carbon already, we can apply the molar mass of carbon to get to the gram of carbon. So that will be the longer method of solving this. And now let's do it. 55.4 grams of C10H14O, and the molar mass of carbon here is 150.1 grams of C10H14O over 1 mole. And now for every 1 mole of carbon, there will be 10 mole of carbon. And now for every 1 mole of carbon, it weighs 12.01 grams of carbon. And when we solve this, the answer will be the same thing, 44.3 grams of carbon. So mathematically here in this case, if we were to do the comparison between the long way and the short way, we are taking this, multiply by 120 divided by 150.1. And in this longer way right here, we still take this, multiply by 10, multiply by 12.01. So in this case right here, the 10 multiplied by the 12.01 will then equal to the 120.1 that we have seen here from the above, and divided by 150 on the bottom denominator. So this is why that the answer overall, they are the same thing.